The Boeing B-17F Flying Fortress, known as Memphis Belle, became famous because its assigned combat crew completed 25 missions over Europe, while the aircraft itself reached its own 25th credited mission 2 days later with a different crew. It was the first United States Army Air Force's heavy bomber to complete 25 missions over Europe and return to the United States for a highly publicized bond tour. That operational milestone established its historical significance and guaranteed its initial preservation. Yet the physical reality of the airframe contradicted that celebrated status. During 59 years in Memphis, Tennessee, exposure to weather, inadequate shelter, and human interference created a severe gap between the bomber's documented identity and its actual condition. By 2005, local restoration efforts could no longer provide a secure long-term path, and the aircraft was returned to the Air Force collection by mutual agreement. Unlike an aircraft that strikes the ground and leaves a verifiable debris field governed by impact physics, this airframe suffered from vandalism disassembly. Kinetic crash dynamics force loads through known structural paths until the metal fails. The resulting fractures provide a readable map of the forces involved. Vandalism disassembly operates without impact logic. Unmonitored human access over 59 years resulted in chaotic structural gaps. Scavengers systematically stripped the cockpit of historical instruments. They removed interior components without regard for the surrounding architecture. During these unauthorized extractions, original wiring harnesses, fittings, and internal equipment could be damaged or removed. Cutting lines and removing interconnected hardware broke the historical and systems continuity of the bomber. Parts that once documented the exact wartime layout of the interior were gone. This localized scavenging destroys forensic integrity differently than a kinetic event. A crashed aircraft retains its components within a debris field, allowing investigators to reconstruct the failure sequence. Scavenged parts are removed entirely from the site, creating an absolute void in the evidence record. Severed connections left the remaining structure behaving in ways original engineers never intended. It was a collection of weakened frames. The recovery team faced a complex documentation problem upon initiating the recall in 2005. They had to evaluate exactly how much original material remained before planning any physical movement. Investigators cross-referenced each physical absence against historical data to measure the remaining baseline. The team had to treat the entire interior as a compromised zone. Recovery personnel now faced a forensic extraction rather than a conventional wreck recovery. Recovery personnel were not pulling a wreck from a deep ocean shelf. They were extracting a massive compromised structure from a public environment. Inspectors had to navigate through the damaged interior to catalog the extent of the missing hardware. They documented how unregulated public access had eroded the aircraft's mechanical baseline and altered the rigidity of the surviving structure. Securing the bomber required understanding exactly what holding strength remained in the surviving metal. The severed control pathways and missing internal fixtures meant that the recovery engineers could not treat the bomber like a complete, healthy aircraft. They had to plan custom handling around the surviving structure and separate primary load-bearing members from damaged or incomplete secondary systems. Those obvious losses established only the first phase of the structural evaluation. The investigators now had to determine how deeply the invisible environment had compromised the underlying load paths beneath the aluminum skin. At that stage, the structural problem became measurable. Supporting an empty weight of 35,728 pounds requires intact structural geometry. That mass must transfer cleanly through the wings and fuselage down to the main landing gear. The missing interior hardware from earlier scavenging compounded a more severe environmental problem. Moisture, humidity, and trapped debris had penetrated an aging static airframe. Water does not always drain evenly from an inactive display aircraft. Drainage paths can clog with debris during long-term exhibition. Moisture could collect in low structural areas of the fuselage and tail, creating conditions for corrosion that required extensive treatment. The environment could initiate atmospheric, crevice, and galvanic corrosion wherever moisture, damaged coatings, and dissimilar metals remained in contact. In the presence of an electrolyte, dissimilar metals can form an electrical path that accelerates attack on the less noble metal. In aluminum aircraft structure, that process can leave white corrosion products, pitting, and local loss of material. Over decades, that hidden degradation could reduce strength in seams, joints, and lower structural members even where the exterior shape still appeared intact. As the metal thinned, the safety margins designed by original engineers slowly vanished. This loss of material dictated the entire scope of the 2005 stabilization effort. Museum technicians could not simply treat the surface metal or patch visible holes. The systemic loss of load-bearing capacity meant the bomber risked structural collapse under static display loads. To arrest the decay, the recovery team established a strict operational requirement. They mandated a total teardown of the machine. Restoration required controlled, evidence-driven disassembly. Technicians removed exterior panels, opened overlapping seams, stripped later paint and contamination, and inspected lower frame connections and mated surfaces where water and debris could have been trapped during the Memphis years. Engineers then mapped the fuselage and wing structure to decide where replacement material was required and where original metal could be preserved and treated. The severity of the decay meant passive display care was not enough. Active corrosion treatment, cleaning, and protective finishing were required before reassembly. Components were separated where necessary to remove hidden corrosion cells between mated surfaces, and the prepared metal was protected with suitable aircraft conservation coatings before it returned to the structure. Once the bomber moved into a controlled indoor environment, new moisture exposure ended, but the stripping process left a stabilized bare metal skeleton with its historical identity temporarily erased. Before final reassembly could advance, investigators had to decide which version of the aircraft they were saving. That procedural boundary triggered the forensic discipline of configuration time locking. The restoration team worked from a selected wartime presentation standard rather than trying to display every phase of the aircraft's long life at once. For a museum aircraft, that choice creates a difficult trade-off. Preserving every historical layer respects the entire lifespan of the machine, but it can create a hybrid artifact that never existed at one moment in service. To protect the aircraft's combat identity, the institutional decision prioritized its wartime appearance over later tour and display layers. The conservation target was anchored to the combat identity associated with May 17, 1943. That day marked the assigned crew's 25th mission. The aircraft itself was credited with its own 25th mission 2 days later, on May 19, 1943, with a different crew. Establishing this temporal boundary forced technicians to actively filter the available physical evidence and historical documentation. The airframe had a rich, documented history immediately following that combat milestone. It returned to the United States and participated in a high-profile stateside war bond tour. During this tour, genuine inscriptions, messages, and later markings were added to the aircraft by people who encountered it far from combat. Those tour inscriptions were authentic historical evidence and were documented, but the selected wartime configuration kept them off the restored exterior so the aircraft would read as a combat veteran rather than a tour artifact. Enforcing this boundary required immense evidence discipline. Every element of the exterior camouflage and interior outfitting was checked against surviving wartime photographs, William Wyler footage, restoration research, and other archival evidence. The team studied these sources to place field repairs, chipped paint, and nose art details as accurately as the record allowed. If a patch, marking, or equipment detail could not be supported by the evidence for the selected wartime presentation, it was left out of the master reassembly plan. The same standard extended deep into the fuselage. Crew stations, oxygen bottles, ammunition feed tracks, radio configurations, and other equipment had to match early 1943 technical orders, with later war upgrades excluded. The decision eliminated the chaotic visual noise of the outdoor exhibition years and the layered modifications of the post-war era. It provided a clear, rigid blueprint for the visual and structural restoration of the machine. However, strictly enforcing this time-locked standard exposed a massive operational vulnerability. Demanding an exact early 1943 combat configuration meant that every missing piece of hardware had to exactly match an early war specification. The team could not simply substitute later readily available bomber parts to fill the structural gaps discovered during the initial evaluation. That boundary immediately created a severe mechanical constraint. The structural skeleton was now ready to receive its historically accurate components, and the exact visual layout was mathematically defined. Executing this precise configuration required moving the fragile structure and confronting a critical hardware shortage. Relocating the fragile bomber from Memphis to Dayton, Ohio by truck created a hard geometry limit, so the aircraft was transported in modular sections across a long public road movement. Moving a machine with a massive operational footprint required careful separation, bracing, and documentation of the major assemblies before transit. Technicians treated each section as a vulnerable artifact, controlling loads so the surviving aluminum structure was not twisted during removal or shipment. The team fabricated custom transport cradles to support the modular sections evenly on the flatbed trailers and isolate the bare aluminum from highway vibration. Distributing the weight properly ensured that the transit forces did not induce new microfractures into the deeply degraded metal. When the trucks reached the secure indoor restoration facility, the airframe was out of the damaging environment but still divided into transport sections. Reintegrating the bomber required resolving the severe internal voids. The strict conservation boundary anchoring the aircraft to 1943 demanded absolute forensic accuracy. This institutional decision immediately triggered a massive supply constraint. The team had to replace the internal hardware lost during the outdoor exhibition years to restore the mechanical continuity of the bomber. Finding correct replacement components proved highly difficult because of the specific subtype of the machine. American factories built more than 12,700 Flying Fortresses during the war. Statistically, this enormous production run might suggest a large supply of salvageable surplus parts. However, model and configuration differences limited what the museum could use. The B-17F represented an earlier wartime standard, while the later B-17G became the most numerous model. Later components could not automatically be substituted into a restoration focused on the Memphis Belle's wartime appearance. The clearest visual divergence sat in the nose. The early F model lacked the powered chin turret associated with the later G model. That absence was more than cosmetic because the nose armament, glazing, fittings, and internal equipment arrangement had to match the chosen F model presentation. A restoration crew could not simply use a later G model nose arrangement without compromising the aircraft's visual and historical authenticity. This part's problem reached beyond the nose. Interior equipment, crew station fittings, wiring runs, and display hardware had to match the F model standard supported by the record. Each missing bracket, control component, or instrument panel still had to be verified before installation. The supply chain for authentic early war heavy bomber components was effectively zero, and the time-lock boundary ruled out quick retrofits of modified later parts. Without compatible donor airframes, the engineering team had to find an alternate way to reconstruct the missing structure. The scarcity of correct early configuration hardware forced a hard decision upon the museum administration. Because not every required physical component could be sourced, the team had to choose between leaving gaps inside the airframe or fabricating missing components. The administration committed to a full restoration for static display. To achieve this, restoration staff fabricated needed parts using surviving documentation, donated material, purchased components, and archival references. This decision solved the immediate supply constraint but initiated a rigorous process of evidence-guided fabrication. Evidence-guided fabrication meant rebuilding missing components from the strongest reliable record available. The crew translated drawings, period photographs, film evidence, and comparable wartime parts into three-dimensional display hardware, cross-checking incomplete sources before committing metal to the airframe. Once a design was supported, the fabrication team matched material, dimensions, and finish as closely as the restoration standard required. Recreating these components pushed the technicians back toward the pace of a wartime aircraft shop. Building or adapting forming tools, shaping aluminum, drilling holes, and checking each part against the surviving airframe before installation. Even a missing bracket, panel, rack, or crew station fitting could require hours of research before it reached the airframe. This meticulous process was applied across the bomber. The team worked through the internal voids, restoring or fabricating crew station fittings, radio equipment supports, electrical conduit brackets, and instrument panel elements as evidence allowed. Integrating these new parts into the original structure required extreme precision. The newly manufactured hardware had to mate seamlessly with the surviving structural stringers. Technicians had to align the pre-drilled holes in the fresh aluminum perfectly with the existing rivet holes in the 70-year-old airframe to avoid weakening the original metal by drilling new paths. Committing to archival blueprint fabrication carried an immense operational cost. Prioritizing historical and structural integrity over project speed consumed vast amounts of manpower. The restoration completely bypassed modern efficiency methods, relying instead on hand-driven craftsmanship. By the time of public display, the restoration had absorbed more than 55,000 labor hours, with some interior work continuing after the aircraft entered the gallery. Much of that labor remained tied to the slow work already driving the project: research, material testing, and hand riveting. The administration chose to endure this extreme labor penalty to guarantee the forensic accuracy of the early war variant. That investment restored much of the bomber's mechanical and visual continuity. The next problem was not whether missing hardware could be recreated, but whether the repaired original airframe could accept it safely under static display loads. For the final phase, the question shifted from repair to permanent support. The teardown had neutralized deep corrosion, but left thousands of stabilized components and fabricated parts to be reassembled under static load conservation. Final assembly for static display demanded careful control of weight, alignment, and long-term support, because the museum was not returning the Memphis Belle to flight. Indoors, gravity would still load the wings, fuselage, landing gear, support points, repaired joints, treated frames, and replacement rivets every day. As reconstructed crew stations, ammunition racks, and radio equipment filled the fuselage, technicians managed hydraulic support jacks to prevent twisting as the balance point shifted. The engineering team then had to physically mate the outboard wing sections back to the central fuselage carry-through structure. This procedure demanded heavy lifting equipment and precise geometric alignment. The custom fabricated internal parts had to integrate seamlessly with the 70-year-old aluminum without forcing the original metal out of alignment. If a main spar was torqued into position while misaligned by a fraction of an inch, the resulting internal tension would concentrate destructive stress on the aging joints. Technicians utilized specialized alignment jigs to hold the massive wing sections perfectly level as they were guided into the fuselage mating slots. Once the attachment hardware seated through the wing and fuselage structure, the connection points were secured under the restoration team's static display requirements. The 4 radial engines were then installed on the wing structure, adding substantial forward weight. The landing gear and support structure were inspected so the restored airframe could carry its own mass safely in the gallery. With the load paths successfully locked, the visual reconstruction could conclude. The structural skeleton was finally enclosed and the exterior surfaces were painted to exactly match the rigid forensic boundary of the early 1943 target date. The paint team applied the documented camouflage patterns, tail numbers, and squadron codes for the target wartime presentation, excluding post-war markings and bond tour signatures. Moving the completed aircraft from the restoration hangar to the exhibition hall marked the final public handling phase. The airframe had to be moved carefully into the gallery in its restored configuration, demonstrating that the completed display structure could be positioned safely without adding a new layer of damage. Achieving this permanent stability required an immense institutional commitment. The comprehensive effort to arrest structural decay, manufacture missing hardware, and reassemble the machine demanded 13 years of continuous restoration. The team successfully converted a rapidly deteriorating outdoor artifact into a structurally sound, historically accurate forensic record. The operation culminated 75 years after the Memphis Belle's assigned crew completed its final combat mission. On May 17, 2018, the fully conserved aircraft was placed on permanent indoor public display within a climate-controlled gallery. The historical asset was secured for long-term exhibition, preserving as much original and wartime material as the evidence and surviving structure allowed.